Hello, in a few moments we'll have example of calculation and derivation of the moments of several random variables, including Gaussian distribution. So the probability density function of a Gaussian distribution is given by this expression, which is basically this is a central distribution. So here, for simplicity, assume that it has a zero mean and a variance of sigma 2. So different moments of this distribution can be calculated. So mean of x to the power of n, mean of x to the power of n, basically as we defined, is equal to integral from x from minus infinity to plus infinity of x to the power of n fx of x dx. So if this n is an odd number, for instance, if x is equal 1, x, so we'll have for x equal 1, I have x fx of x. So this function is odd, which is if you plot it, you will get an expression, a curve like that, and you see like that. So if you calculate the integral from, let's say, minus t to plus t of this function, this area and this area, they are equal to negative of each other. So this integral from minus t to plus t dx, this area is equal to 0. Now you can let these t and this minus t to simultaneously go to plus and minus infinity respectively. So this integral is obviously equal 0 if n is odd. Now, if n is even, then we have to do integration by part, alternatively to calculate. So if n is equal to 2, so if I have integral of these, so I have mean of x to the power of 2, so this is integral of x to the power of 2, fx of x dx, x is equal to minus infinity to plus infinity. Calculation of this integral, if you don't know the expression, is hard, but we have solved this problem before, and is obviously equal to sigma 2. Which shows that this expression is correct, because if n is equal to 2, so k is 1, and then you get sigma to the power of 2, and then you have 1 times, and here is n equal to 1. So you have 1 times, you don't have these terms anymore. So it's kind of like now if you put n equal 4, mean of x to the power of 4, you get 1 times 3, and then you get sigma to the power of twice times 2, which is equal to 4. So which is equal to 3 times sigma to the power of 4. So this expression is very important. Now, absolute moment, if you put absolute value, the difference, these two expressions are identical, because if n is even, x to the power of n is equal to x to the power of n if n is even. So for even, I have exactly the same expression here. But if n is odd, this integral of x absolute value to the power of n from minus infinity to plus infinity, fx of x dx, this is still an even function. So it's not going to be equal to 0, unlike this case. You can easily show that this expression is correct. Exercise. So for n equal 4, so you can use this expression or this expression. So for a Rayleigh distribution, which is often encountered in many engineering applications such as communication or signal processing, the Rayleigh distribution is a function like that. So this is a PDF. So if you want to plot the PDF, you have a function like that. So it has 2 terms. So you have a expression which is initially like a line, okay, but then it will k. So this area is equal 1. So the moments of this distribution are given by integral of x to the power of n, and then you have x divided by alpha 2, and then e to the power minus x2 divided by 2 alpha 2, and then dx. X start from 0 to plus infinity. Remember that this is a non-negative random variable. So you can calculate these moments because we had using the normal integral, because in the previous slides we had similar integrals. So those integrals can be calculated easily. So for odd and even n, we have different expressions. So this expression can be obtained using the expressions that we had for the moments of normal random variable, using the expressions of moments of a normal random variable in the previous slides. For example, if you put n equal 1 here, so if you put n equal 1, k is equal 0. So if k is equal 0, all these guys disappear, and here you get n to the power of 1, so you get alpha, and then you get square root of pi over 2. Or if you put n equal 2, so you get this expression. So you get k becomes equal 1. So you get 2 to the power of 1, and then you get 1, and then you get alpha to the power of 2. So you get mean of x to the power of 2. You get twice alpha to the power 2. But variance sigma 2 of x is equal to mean of x to the power of 2 minus mean of x to the power of 2, because we have already these guys. So you put this one here, and you put this one here, and then you get this expression. So we can find similar expression for other distributions. So this is called a Maxwell distribution. For Rayleigh, instead of x2, we had x, and this constant was different. Okay, so Maxwell distribution is also encountered in physics and so on. So the moment of order n, if n is even, is given by this distribution, and if it is odd, if it is even, given by this one, if it is odd, and then for even are given by this. But again, these moments can be, this expression can be obtained using the expression of the moments for Gaussian distribution, because basically you have this same part of Gaussian but plus something extra here. In particular, if n equal 1, so the mean of a Maxwell distribution is similar to Rayleigh. In the Rayleigh we didn't have these two here, and then instead of this one we had pi, the other one. The expression is slightly different, and here you can calculate, and then using these two we can calculate sigma 2x, which is going to be equal to 3 times alpha 2 minus this guy to the power of 2, whatever it is, you put it here. So you get alpha 2 times a constant, which is equal to 3 times minus minus 4 times or 8 over pi or whatever.